In the name of Almighty God, I'm Master Hassan Kashi, and today I want to talk about radio frequency coil. A RF coil is a component in magnetic resonance imaging or MRI machines that acts as the system's antenna. It functions to transmit a radio frequency or RF pulse to excite nuclear spines within the patient's body and then receives the resulting RF signal for image formation. RF coils are crucial for data quality and come in various designs, such as surface coils for small body parts and birdcage coils for the head, with different types serving receive only, transmit only, or combined transmit and receive functions. And how it works. The first one is transmission or TX. The RF coil broadcasts an RF pulse to patient. The next one is excitation. Their pulse excites the nuclear spines in the body, causing them to align and then rotate. The next one is reception or RX. The RX coil then acts as a detector, receiving the weaker RF signal, the MR signal, as these excited spines return to their equilibrium state. The next concept is signal processing. This signal is processed by the MRI system to generate an image of the internal body structures. And what are the key characteristics? The first one is tuning. RF coils are tuned to specific frequencies to maximize their efficiency. The next one is inductance and capacitance. They typically form an LC circuit using the inductance of the coil wires and added parallel capacitance. The next one is antenna function. They serve the same role as an antenna, both broadcasting and receiving signals. And what are the types of radio frequency coils? The first one is surface coils. Simple loop coils, circular or rectangular, placed over a specific body part, limited to a relatively shallow depth of imaging. The next one is birdcage coils, a specific type of RF coil with a birdcage-like structure that provides high radio frequency homogeneity, often used for head imaging. The next one is transmit receive or TR coils. A single coil used for both transmitting the RF pulse and receiving the MR signal. Receive only RX or coils. Coils designed solely for detecting the MR signal while a separate body coils act as transmitter. The next one is coil arrays. Multiple smaller coils arranged together to improve signal to noise ratio and enable faster imaging through parallel imaging techniques. Actually, radio frequency coils or RF coils are the receivers and sometimes also the transmitters of radio frequency RF signals in equipment used in magnetic resonance imaging or MRI. The MR signal in MRI is produced by the process of resonance, which is the result of radio frequency pulses. They consist of two electromagnetic coils, the transmitter and receiver, which generate the field and receive the resulting signal. Atomic nuclei of interest in MRI studies have their own resonance frequencies in the radio frequency portion of the electromagnetic spectrum. Although the electromagnetic fields produced by the transmitting coil are in the RF range of 10 of megahertz, often in the shortwave radio portion of electromagnetic spectrum, at powers usually exceeding the highest powers used by amateur radio. There is very little radio frequency interference produced by the MRI machine. The reason for this is that the MRI is a poor radio transmitter and lacks of an antenna. The radio frequency electromagnetic field produced in the transmitting coil is a magnetic near field with very little associated changing electric field components such as all conventional radio wave transmission have. Thus, the high-powered electromagnetic field produced in the MRI transmitter coil doesn't produce much electromagnetic radiation at its radio frequency, and the RF power is confined to the coil space and not radiated as radio waves. Thus, the transmitting coil is a good EM near field generator at radio frequency but a poor EM radiation transmitter at radio frequency. The receiver coil picks up the oscillation at RF frequency produced by precision of the magnetic moment of nuclear inside the subject. The signal acquired by the coil is thus an induced EMF and is not the result of picking up radio waves. This is a common misconception and unfortunately has propagated through the literature. MRI scanners are generally situated in metal mesh-lined rooms which act as Faraday cages. And what are the types? RF coils for MRI can be grouped into two different classes, volume coils and surface coils. Volume coils are designed to provide a homogeneous RF excitation across a large volume. Most clinical MRI scanners include a built-in volume coil to perform whole-body imaging, and smaller volume coils have been constructed for the head and other extremities. Common designs for volume coils include birdcage coils, TEM coils, saddle coils, and two-dimensional cylindrical high-pass ladder. These coils require a great deal of RF power because of their size. So they are often driven in quadrature in order to reduce by 2 the RF power requirements. The condition to attain a high RF magnetic field homogeneity is to approximate spatial causing current distribution in a radio frequency coil. The RF homogeneity of volume coils is highly desirable for transmission, but is less ideal when the region of interest is small. The large field of view of volume coils means that they receive noise from the whole body, not just the region of interest. The next one is surface coils. Surface coils are designed to provide a very high RF sensitivity over a small region of interest. These coils are often single or multi-turn loops which are placed directly over the anatomy of interest. The size of these coils can be optimized for the specific region of interest. Surface coils make poor transmission coils because they have poor RF homogeneity even over their region of interest. Their small field of view makes them ideal as receivers as they only detect noise from the region of interest. Radiofrequency coils are an essential MRI hardware component. They directly impact the spatial and temporal resolution, sensitivity, and uniformity in MRI. Advances in RF hardware have resulted in a variety of designs optimized for specific clinical applications. RF coils are the antennas of the MRI system and have two functions. First, to excite the magnetization by broadcasting the RF power TX coil, and the second, to receive the signal from the excited spine or RX coil. Transmit RF coils emit magnetic field pulses or B plus 1 to rotate the net magnetization away from its alignment with the main magnetic field B0, resulting in a transverse precessing magnetization. Due to the precision around the static magnetic field, the magnetic flux in the received RF coil or B-1 changes, which generates a current I. This signal is picked up by an antenna and pre-amplified, usually mixed down to a lower frequency, digitalized and processed by a computer to finally reconstruct an image or a spectrum. Transmit and receive functionality can be combined in one RF coil or TX-RX coils. This review looks at the fundamental principles of an MRI-RF coil from the perspective of clinicals and MR techniques and summarizes the current advances and developments in technology, starting with the initial studies by literature has been a tremendous growth as a diagnostic and research imaging modality. MRI offers excellent soft tissue contrast at high spatial and temporal resolutions with the ability to have a three-dimensional tomographic representation of the subject of interest. MRI is unique in its ability to move beyond anatomically imaging as it allows visualizing metabolic functions and chemical processes via spectroscopic imaging and offers advanced methods to measure physiologic properties such as tissue oxygenation, flow, diffusion, and perfusion, while advances in the MRI hardware such as increased field strength and improved gradient performance have been substantial. Advances in the radiofrequency RF technology have also proved to be valuable to improve the resolution and shorten the duration of MRI examination. MRI RF coils are essential components for every MRI examination as they are responsible for the excitation and reception of the MRI signal. Basic concept and terminology of MRI RF coils are explained, and a broad overview of the application field has been given. Then, in an in-depth explanation of current state-of-the-art transmit and receive RF coils is given, and novel technologies, approaches, and current advances in the field of MRI RF coils are discussed in this part. And what are the basic concepts and overview transmit and receive RF coils and basic terminology? Every MRI system, as you can see in this left picture, is a mix of several subsystems that each provide necessary functionality to generate image of an object. In general, RF coils act like a broadcasting station. They transmit and receive signals. As a patient is positioned in an MRI scanner, the tissue obtains a small magnetization that aligns with the magnetic fields M0. A RF transmit coil or TX generates an RF pulse that produces a small magnetic field perpendicular to the magnetic field, which rotates net magnetization away from its alignment with the main magnetic field. The stronger the RF pulse energy, the further the magnetization will tilt or flip, which is called the flip angle or theta. The RF receive coil or RX detects the precessing magnetization resulting in an induced electric current via the electromagnetic induction. The induced current is the MR signal and represents the mixture of magnetization from the tissue within the field of view or FOV of the RX coil. RF coils may serve as transmitters, receivers, or both. When used as transmitters, RF coils generate an oscillating, rotating magnetic field denoted B1 that is perpendicular to the static main magnetic field or B0. If the oscillation of B1 closely matches the natural precessing of nuclear spines near the Larmor frequency, energy is deposited into the spine system, causing a change in its net alignment. The B1 field is generated by the transmit RF coil in response to a powerful current generated by the scanner's transmit circuit. Wave-1 is typically turned on for only brief periods of time, a few milliseconds, called RF pulses. By adjusting the magnitude or duration of these B1 pulses, the nuclear spine system can be rotated by variable flip angles such as 90 degrees or 180 degrees. When used as receivers, RF coils are responsible for detecting the MR signal. The oscillating net magnetic flux from the excited spine system can be captured by the coil in which an induced electric current is generated. This current is then amplified, digitalized, and filtered to extract frequency and phase information. Today, RF receive-only coils are often collected into large arrays for use in parallel imaging applications. Auto RF coils serving both transmit and receive functions were once the norm. Today's modern scanners mostly utilize separate transmit and receive systems. However, some special parts transmit receive RF coils are still in common use, especially those used for head and knee imaging. Here you can see the patient inside the MRI scanner, and you can see B1 and B0 magnetic field. And here you can see that I have used electromagnetic as a physical module, and you can see electric field here and the plot for parameter, and here reflection graph. Thank you so much for watching my video until the end. You can also download a radio frequency coil from my GitHub at master script address.